Let's start off our study in physics by looking at vectors. So vectors have a length and a direction, whereas scalars only have a length. So if we consider the motion of a particle in one dimension, we have this unit vector I, which has a magnitude or length of 1 unit, and it points to the right. And this is used to represent different vectors in one dimension. So for example, the position vector is equal to x multiplied by I. So the position vector is a special type of vector that's measured from the origin, and this negative sign tells us that the position of the particle is 2 meters to the left of the origin. And another example vector is the velocity of the particle. So this tells us the speed and the direction in which the particle is traveling. That's also represented as follows, with a negative sign meaning that the velocity points to the left or west. And examples of scalar quantities or numbers are speed, distance, and so on. So these have a magnitude but no direction. We can represent the motion of a particle using this motion diagram or a graph of the position versus time. And choosing some interval of time, the displacement of the particle, which is a vector quantity, is equal to the final position in that interval minus the initial position in that interval. And because we're looking at one-dimensional motion, we usually drop the arrow, and it's implied that the displacement's a vector. So for example, between 0 and 6 seconds, the displacement of the particle is minus 8 minus the initial position, so what we get is minus 6 meters. So effectively the particle is displaced 6 meters to the left. And we can put a positive 6 meters and write west, or to the left. Now in contrast, the distance that the particle's travelled is a scalar quantity. So it starts from minus 2 meters and goes to 4.3 meters, and then from 4.3 meters it travels to minus 8 meters. And the distance is a scalar quantity, so it has no direction. The average velocity of a particle is a vector quantity, and it's equal to the displacement on a change in time. So for example, from 0 to 6 seconds, the final position is minus 8 minus the initial position, which is minus 6 meters, on a change in time, which is 6 minus 0 seconds. And therefore we obtain minus 1 meter per second for the average velocity, meaning that on average the velocity of the particle is to the left or pointing west. Now average speed, on the other hand, is equal to the distance on time. So between 0 and 6 seconds, the particle travels from minus 2 to 4.3, so that would be 6.3 meters, and from 4.3 to minus 8 is another 12.3 meters. So that will be 18.6 meters travelled in total over the time, which is 6 seconds, which is an average speed of 3.1 meters per second. So note that this is a scalar which only has a magnitude and no direction. Recall that the average velocity is equal to the displacement on the change in time. And it's implied the displacement and the average velocity are vector quantities, so we don't have to draw the arrows. Now if we take the limit as delta t approaches 0, we obtain the instantaneous velocity. So the instantaneous velocity is the first derivative of position with respect to time, or the slope of the tangent to the position time curve at a particular point in time. So here the velocity is positive, so it points to the right or east, and the instantaneous velocity is 0 at 2.5 seconds, and from 2.5 to 6 seconds, the instantaneous velocity is negative, or points to the left, which is consistent with the velocity time graph here. And you can obtain this graph by differentiating the position with respect to time. Now the instantaneous speed is the magnitude or length of the instantaneous velocity, so it's always positive and it's a scalar quantity with no direction. The average acceleration is the change in velocity on a change in time. So for example, between 0 and 6 seconds, we have minus 7 meters per second, minus 5 meters per second, over 6 minus 0 seconds. So that gives us an average acceleration of minus 2 meters per second. So on average, the acceleration vector points to the left or west. Now the instantaneous acceleration is obtained by taking the limit of the change in velocity on a change in time. So therefore the instantaneous acceleration is the first derivative of velocity with respect to time, which is a constant acceleration, meaning that at any point in time, the acceleration vector points to the left. Now at this point in time, the velocity points to the right or east, and at this point in time, the velocity points to the left or west. So therefore, because the velocity vector is against the acceleration vector here, the particle is decelerating, and at this time the particle is accelerating. The big 5 kinematic equations are used to predict the motion of a particle where the acceleration is uniform or constant. So using this velocity time graph, which is linear, delta x, which is the displacement or change in position of the particle from time 0 to time t, is equal to the area under the velocity time curve. Now similarly, equation 2 is obtained by the area under the acceleration time curve, so the change in velocity is equal to the area of the rectangle. And similarly, the third equation is obtained again by the area under this curve, but this time we break it into a rectangle and a triangle. And now if you substitute v minus v naught, and to obtain the fourth equation, we solve this equation for the time. And now if you substitute for t into equation 1, now to obtain a fifth kinematic equation, we solve this equation for v naught, and then substitute v naught in equation 3, and that gives you the fifth kinematic equation. For problems where the acceleration is non-uniform, so the acceleration may be a function of time, or a function of velocity, and so on. So in this case, we need to use our differential equations for the instantaneous velocity and acceleration. So differentiating the position with respect to time, we get the instantaneous velocity at some time t, or the slope of the tangent to the position time curve at time t. And if we differentiate again, we obtain the instantaneous acceleration. So for a non-uniform acceleration, we need to separate the variables and integrate both sides. So effectively, the area under the acceleration time curve from time 0 to time t is still going to give us a change in velocity between time 0 and time t, except obviously the velocity will not be linear in this case. And similarly, the area under the velocity time curve gives us a displacement, or the change in position, between time 0 and time t. To select which kinematic equation we should use in uniform acceleration problems, one factor is how many intervals of motion we have. So if we consider this elevator, it first accelerates, then it coasts at a constant speed, and then it decelerates and goes back to rest. And what we do is draw a coordinate system, so we have a direction and an initial position of the elevator. And where it starts from rest, we have an initial velocity of 0. Now if we want to determine the total time that the elevator takes to get to the top of the building, where the building has a height h, well, in the first interval of motion, we have the initial velocity, we have the final velocity in that interval, which is the coasting velocity, and we're given an acceleration, so we can use this kinematic equation to solve for the time. And in the third interval, so using symmetry, t3 is equal to t1. And if we're given the height of the building, think about how you'd find the time taken for the elevator to coast through the second interval. Another consideration when we're selecting which kinematic equation to use in a uniform acceleration problem are the number of objects involved in the motion. So we first select our coordinate system, including the origin. So the x direction, and x0 is equal to 0 at the origin. Now suppose we want to find a position where these cars collide, and we're given the initial position of each car, we're given the initial velocity of each car, and we're given the acceleration of each car. And suppose car A is not accelerating. So given what is known, we can use this kinematic equation and apply it to each car, where the acceleration of car A is 0, and then you apply a constraint, so the positions must be equal, and then you can solve the resulting equation to obtain the time of the collision, and from that you can substitute the time into either of these equations to obtain a position of the collision. The following equation describes the position of the particle as a function of time. So in part A, the average speed is distance on time, so the position is positive and increasing with time, while the total distance travelled between 1 and 3 seconds, and that's divided by the time of the interval. So the average speed is a scalar, so it'll be positive and have no direction. Now the average velocity, on the other hand, is a displacement on a change in time. So you can see that these are identical, except the average velocity has a direction. So if you get a positive answer, the velocity vector points to the right. Now to find the instantaneous speed, we first find the instantaneous velocity, and then if you substitute 1.5 seconds, and the instantaneous speed is obtained by taking the magnitude of the instantaneous velocity at 1.5 seconds. And speed's a scalar quantity and has no direction. And in part C, the acceleration, so really think about your units based on what you're given in the problem. Given x of 0 is 0 and the velocity at 4.5 seconds is 0, we're asked to find the displacement and distance from 0 to 5 seconds. So the displacement is the area under the velocity time curve. So that would be the area under this trapezium plus the area under this triangle minus the area under this triangle which will give you 12 meters. And the total distance traveled is simply the sum of all these areas. So that would give you 12.5 meters. And for part B, the average speed is equal to the total distance traveled over the total time, which is 2.5 meters per second. And the average velocity is equal to the displacement over the change in time, which is 5 minus 0 seconds, or 2.4 meters per second. Sketch the position versus time graph from this velocity time graph. And taking our initial condition of x of 0 is 0. Well, the velocity gives the slope of the tangent to the position time curve. So if the velocity is linear, then the position versus time curve is parabolic. And from 0 to 2 seconds, the velocity is increasing and positive, so therefore the slope of the tangent to the curve is going to increase. Now from 2 to the time when the velocity is 0, the velocity is decreasing. So therefore the slope of the tangent to the position versus time graph is decreasing, but still positive until we reach the maximum. And then thereafter the velocity is negative, so the slope of the tangent to the position versus time curve becomes negative, and it's still parabolic until we reach 5 seconds, where the velocity is constant. So therefore the position versus time graph becomes linear, because the slope here is constant. A basketball is thrown vertically, and assuming freefall conditions with the following gravitational acceleration, part A asks us to find the maximum height of the ball. So what we do is choose a coordinate system with an origin at the initial position of the ball and a positive direction. So here we have a single interval of motion because it has the same uniform acceleration. So the maximum height of the ball is h. And we know that at the maximum height, the velocity of the ball is 0. So therefore we know the following quantities, and we can solve for the maximum height of the ball using this kinematic equation. And for part B, we're asked to find the time that the ball is in the air. So we can solve for half the time from the launch of the ball to the top of the trajectory where the velocity is 0. And we also know the acceleration is minus g. So that gives us 1/2 of the time that the ball is in the air. And by the symmetry of the problem, the ball comes back down in the same time. So post your answer in the comments and feel free to ask questions if something's not clear. A spring launches a ball at some initial velocity, and we're asked to find the time taken for the ball to fall into a bucket that's placed 2 meters below its initial position. So we recognize that the acceleration is uniform, so we can treat this as one interval of motion. So choosing our coordinate system, we'll have the positive y direction and the origin at the initial position of the ball, and the final position is thereby minus 2 meters. So knowing the initial position, the final position, the initial velocity, and the acceleration, which is minus g, given our positive y direction is upwards, you can solve for the unknown time t using this kinematic equation, and you'll get 2 solutions to choose from by solving the quadratic. And post your answer in the comments, and also your questions if something's not clear. A helium balloon is released and floats in the air to a height h with a constant acceleration a. Assuming that the total travel time is greater than 4 seconds, how much further does the balloon travel in the last 2 seconds than the first second? So the kinematic equation to use is y equals y0 plus v0 t plus 1/2 at squared, and we have y0 is equal to 0 as our reference point, and v0 is equal to 0 as the balloon is released. So what we can do is take h1 is equal to 1/2 a by 1 second squared, h2 is equal to 1/2 by the acceleration by t minus 2 squared, and h is equal to 1/2 at squared. And then subtracting these two, we get this distance of the interval, and then we can subtract h1 from this result to obtain the answer. A car is travelling at initial velocity v0 and an acceleration given by the following equation, which accounts for air drag, so there's going to be air resistance impeding the motion. And k and m are constants, and v is the instantaneous velocity of the car. And we're asked to derive an expression for the velocity as a function of time. So given that the acceleration is non-uniform, we can write it as the instantaneous rate of change of velocity with respect to time. And that gives us a differential equation where we separate the variables and integrate both sides to obtain the following expression. And now we can apply our initial condition where the velocity at time 0 is equal to v0, and that'll give you the constant of integration, and using some algebra, you can obtain an expression for the velocity as a function of time. And post your answer in the comments. A skydiver opens his parachute, and from this instant, he has an initial velocity v0 and an acceleration given by the following equation, which accounts for air drag. So we have a gravitational acceleration and a term that accounts for air resistance, which is a function of the velocity. So g, k and m are constant, and v is the instantaneous velocity of the skydiver. And we're asked to derive an expression for the velocity as a function of time. Well, given that the acceleration is a function of velocity, it's non-uniform, so writing the acceleration as the instantaneous rate of change of velocity with respect to time, and separating the variables, and integrating both sides of this equation, you can use u substitution to evaluate the integral on the left-hand side, and on the right-hand side, it's straightforward. So evaluate the integral, apply your initial condition, where the velocity at time 0 is v0, to find the unknown constant of integration, and post your expression for the velocity as a function of time in the comments. An elevator starts from rest and travels up a 400 meter tall building. And we can make the following assumptions, and now we can choose our coordinate system. So here we have a time of t equals 0, and we break this up into 3 intervals of motion. So to find the total time taken for the elevator to reach the top of the building, so in the first interval we can use this kinematic equation. So this is the same as t1 minus 0, which is equal to delta t1. And by symmetry, that's equal to delta t3, which is t3 minus t2. Now to find delta t2, we can use the height of the building, which is equal to the sum of the distances travelled in each interval. So to find delta y1, which is equal to y1 minus y0, we can use this kinematic equation, because we've already found delta t1. And by symmetry, delta y3 is y3 minus y2, which is equal to delta y1. And from this equation, we can find delta y2 and substitute it into this equation with the coasting velocity, and that gives you delta t2. Projectile motion is a common type of motion you'll encounter in 2 dimensions, and to simplify things, I've taken the origin at the position of the projectile. So the projectile is launched from a position of x0, y0 at an initial velocity v0. And what we do is resolve this vector into these x and y components using the unit vectors. So we can write the initial velocity vector, and this is using vector addition. And using trigonometry, so projectile motion assumes that the projectile or particle is under the influence of gravity with no air resistance. So therefore in the horizontal direction, we only have one kinematic equation, so there's no acceleration component in the horizontal direction. Now in the vertical direction, we have the same kinematic equations that we've derived previously for 1D motion, and we can replace the x's with y's, and the velocity component will be in the y direction. A ball is launched from the ground with an initial velocity v and angle theta, and lands on a platform at a height h and distance l. And we're asked to derive an expression for h in terms of these variables. So what we have is h is equal to the vertical component of the initial velocity by time minus gravity by time squared on 2, and l is equal to the horizontal component of velocity by t, which implies that t is equal to l on v cosine theta. And now substituting the second equation into the first, what we get is h is equal to v sine theta by l on v cosine theta minus g on 2 by l squared on v squared cosine squared theta. And doing some cancellations and having sine theta on cosine theta is tan theta, you get your final expression. A baseball is launched at an initial velocity of 30 meters per second at an angle of 60 degrees from the horizontal axis. And we're asked to find the maximum horizontal distance of the ball. So choosing our coordinate system, where the origin is at the initial position of the ball and the positive directions as shown, and we want to find the range of the projectile, so that will be x equals r. So there's only one kinematic equation in the horizontal direction, so that will be r is equal to 0 plus the horizontal component of the velocity multiplied by time. So remember that we can resolve the velocity and use trigonometry to find the magnitude of those components. And now we need an expression for the time t, so we'll use this kinematic equation because the initial y position of the ball is equal to the final y position, and we have the vertical component of the velocity and minus the gravitational acceleration by t squared on 2. So we can factor out t, solve this equation, and substitute for t to find the range of the projectile. A projectile is launched at an initial speed v0 and an angle theta, and we're asked to find the angle that maximizes the range. So if we take a coordinate system with the origin at the initial position of the projectile, so the range is x equals r. And the only kinematic equation in the horizontal direction is this one. And to obtain the time t, we can use this kinematic equation because the final position is equal to the initial position, and plus the vertical component of the velocity by time minus gt squared on 2. So factoring out t equals 0 at the initial position of the projectile, and this expression is equal to 0, which gives us the time when the projectile is at its range. And now we can substitute for the time here, and now we can use our trig identity. So the range is maximized when sine 2 theta is equal to 1, meaning that theta is equal to pi on 4, or 45 degrees. A basketball is thrown at a velocity v0 and an angle of 50 degrees, and the distance and height of the throw are shown below. Find the launch speed for the ball to hit the hoop. So what we can do is take our origin at this point with the positive x and y directions as shown. So given that we have the horizontal distance and the angle, we can use this equation. And we also have the initial and final position of the throw, so we can use this kinematic equation in the vertical direction. And now you can solve this equation for t, and substitute for t into this equation. And you can see that v0 cancels, and then you can easily solve this equation for the launch speed. A projectile is launched at an initial velocity and an angle theta. Derive an equation for the range in terms of the following constants, given that the velocity is nonlinear. And you may recognize this exponential decay as drag in the horizontal direction. So here we're accounting for horizontal wind resistance. So therefore the acceleration is also non-uniform, and this kinematic equation in the horizontal direction does not apply. So we write the velocity as a derivative of the horizontal position with respect to time, and solve this differential equation by separating the variables and integrating both sides, and we can use definite integrals instead of solving for a constant of integration. And evaluating these integrals, and x0 is 0 at the origin, and x equals r, which is the range. So what we get is the following expression. And now you can use one of the kinematic equations in the vertical direction to obtain an expression for t, and write the range in terms of the above constants. And post your answer in the comments.